You know that carbon NMR is a really powerful tool for assigning structures to organic compounds. And the key information that we get from carbon NMR is the number of types of carbons, and we can deduce significant information about the functional groups that are present by looking at the chemical shifts of each of the types of carbons. What you'll now learn is that Proton NMR gives you that kind of information plus two more very important things, making it a much more powerful tool for structure assignment than carbon NMR. There are a lot of similarities, and let's look at the key aspects of Proton NMR, and you'll see they look a lot like what we said about carbon NMR. Like carbon NMR, Proton NMR uses very long wavelength, really low energy electromagnetic radiation. Like carbon NMR, we put a sample in an NMR tube. We look at the whole sample at once. That's many, many molecules. There's limited sensitivity, but better than carbon NMR. And that's because with carbon NMR, we're only looking at 1% of the isotope. All the rest is carbon-12 and we don't see it. With Proton NMR, 99.9% of the hydrogen is protium, so we see almost all of it, which helps a lot with the sensitivity. And then beyond that, Proton NMR is inherently more sensitive than carbon NMR. So put the two together and Proton NMR is substantially better sensitivity. The sample is not destroyed, and we obtain qualitative information. Very seldom it's used for quantitative work. So we're basically answering the question of what is something, not how much of it is there. And for the qualitative information, we will see number of types of H's, the number of each type of hydrogen, the actual number of protons of each type. You recall we can't do this with carbon NMR, so this is a huge improvement. We will get chemical shift information from which we deduce information, the functional groups present. Like carbon NMR, we'll learn something about which functional groups are present, and we'll learn something about their relative proximity. The totally new type of information that Proton NMR gives us is which hydrogens are neighbors, which hydrogens are located on neighboring carbons. This is extremely powerful. Let's look at some spectra to illustrate the use of Proton NMR for structure assignment. Here's a spectrum taken from the SDBS database again of the compound we looked at for carbon NMR. You recall in carbon NMR we saw 4 signals because there are 4 different types of carbon. In Proton NMR we'll see 3 types of protons. Remember that this is a methyl group, so we'll put the 3 hydrogens in there maybe just to remind us that A is a signal from 3 hydrogens, B is a signal from 2 hydrogens, and C is a signal from 3 hydrogens. We call the larger chemical shifts downfield, and these numbers in parts per million are called chemical shift. You see several signals here. Well, let's take a look at that. These 3 signals together account for 1 type of hydrogen. The hydrogen that's most upfield, the one that's furthest away from the carbonyl group. So that would be C. So these guys are C. This large signal here, all by itself, is this methyl group that has no neighboring hydrogens. I'll talk about that in a minute. So this is A. And like carbon NMR, alkyl groups move a signal downfield a little. So the protons adjacent to the carbonyl group that also have a carbon attached are shifted a little bit downfield relative to the others. So this is B. This lone signal here is known as a singlet. It isn't split by any neighbors, and by splitting we mean the signal is turned into more than the single signal. Whereas here, this signal is turned into 3. So this would be called a triplet because it's 3 signals. And this guy is 4. The small signals on either side count 2. It's not an equal intensity 4 signal pattern, but rather the signals on the outside are smaller than the ones on the inside. This is called a quartet, 4 signals. Now, what's the explanation for this? By the way, this is B. The formula for the number of lines we see for that certain type of hydrogen equal the number of neighbors plus 1. So, for example, when we look at the signal for B, there are 3 neighbors. 3 plus 1 is 4. The signal for B should be a 4-line pattern, the quartet we see here. When we look at the signal for C, it has 2 neighbors. 2 plus 1 is 3. That signal should be a 3-line pattern, a triplet. Now take a look at this. There's one more type of information that we get from this NMR spectrum, and that is the number of protons that account for the signals we see. This is from a type of information called integration, which the machine does for you, and you can determine exactly how many protons account for each of these signals. In the case we're looking at here, this is 2 hydrogens, this is 3 hydrogens, and this is 3 hydrogens. This 3 hydrogen for A corresponds to a methyl group that has no neighbors. So by looking at the number of protons that account for this signal, and also noticing that it's unsplit, we know that this guy here comes from a methyl group having no neighbors. Very, very powerful. We know that this comes, because it's 3 hydrogens, from a methyl group, and it's a triplet, so it has 2 neighbors. Finally, this is a 2 hydrogen signal, so it's a CH2 group. And it's a 4-line pattern, meaning it has 3 neighbors, and the 3 neighbors must be, wouldn't you guess, a methyl group? So look what we can do. A CH2 group that has 3 neighbors, and a CH3 group that has 2 neighbors. We can put these 2 guys together and deduce presence of an ethyl group. So now you see we have 3 types of hydrogens. A methyl group by itself, coming in a region that is characteristic of being next to a carbonyl. We have an ethyl group with a CH2 coming in a region that is characteristic of being next to a carbonyl. This pretty much nails down the structure. Let's look at another example. Again from the STBS database, looking at a structure as we did for the carbon NMR of acetophenone. 3 hydrogens, all on the same carbon, all have the same signal. 1 hydrogen here and a hydrogen here. These are totally equivalent. In terms of position, these guys are different, but they're equivalent to each other. And then ultimately there's another hydrogen that's different. We have 3A, we have 2 HBs, we have 2 HCs, and we have 1 HD. These 3 hydrogens have no neighbors, so they should come as a singlet at a region or chemical shift that says it's probably near a carbonyl. Look at this. Perfect. Now I can tell you that the integration for this signal is 3H compared to the integration for this signal is 5H. In theory, you can measure this from the spectrum, but in reality, we usually ask the NMR to tell us what the ratio of these signals is. And I put 5H together because you see this is sort of a messy pattern. We have what looks to be probably 2H, 1H, and 2H. So that would be very possibly HB, 1H, it would be D, and then this one would be C. I guessed B for the one that's downfield because it's closest to the carbonyl group. So I'm guessing that makes a shift relative to the other 2 that's downfield. But in any case, we can see that the ratio is 2 to 1 to 2, which makes perfect sense for this aromatic structure. 2 protons that are equivalent, 1 proton that is different from all the others, and 2 other protons that are equivalent. At the same time, we have a singlet methyl group, and this chemical shift suggests they're next to a carbonyl. It is almost impossible to miss the structure assignment here as being acetophenone. So you see that the proton NMR spectrum is terribly powerful. In addition to telling us the number of types of hydrogens and the chemical shifts of those types, which gives us some information about functional groups, it tells us exactly how many hydrogens, in a relative sense, account for each of these signals we observe, and it tells us which protons are neighbors to which. By the way, we didn't do that analysis for this pattern because that's too difficult. These guys are not separated enough for us to really see the splitting that we would expect to see if we were able to sort that out. Okay, It should be clear that proton NMR spectroscopy is a tremendous tool for structure assignment.